अस्सलाम वालेकुम। अ, इस लेक्चर के अंदर हम डिस्कस करेंगे रिलेशन बिटवीन द स्पेसिफिक कंडक्टेंस एंड इक्विवेलेंट कंडक्टेंस एंड आल्सो वी विल डिस्कस अबाउट द मेथड्स टू मेजर द कंडक्टेंस एंड सेल कांस्टेंट। यहाँ पे देखें, कंसीडर देयर वी हैव रेक्टेंगुलर मेटालिक वेसल with the opposite sides exactly 1 centimeter apart. If 1 cubic centimeter of the solution is now placed in this vessel's area of the area of the opposite faces of the cube covered by the solution will be 1 square centimeter. Now, if 1 cubic centimeter of the solution is placed in the above vessel containing 1 gram equivalent of the electrolyte, then the measured conductance will be equal to the equivalent conductance, which is lambda is equal to K. Uh, Now, if we dilute this 1 cubic centimeter of the solution to 10 cubic centimeter by adding 9 cubic centimeter of pure solvent, so the equivalent conductance will be 10 times as specific conductance, because now we have diluted the solution, so lambda will be equal to K into 10. If the solution containing 1 gram equivalent of the electrolyte is dissolved in V cubic centimeter of the solution, then lambda will be equal to K into V. So the equivalent conductance lambda is equal to specific conductance K into volume of the solution in cubic centimeter containing 1 gram equivalent of the electrolyte, which is represented as V. And now we can see the relation between molecular conductance and specific conductance. Uh, the relation which exists between molecular conductance and specific conductance is similar to the relation which we just discussed between the equivalent conductance and specific conductance. So we can see the relation mu V is equal to K into V. Molecular conductance, same like we have seen the equivalent conductance and specific conductance. Here we see that molecular conductance is equal to specific conductance into volume of solution in cubic centimeter containing 1 gram mole of the electrolyte. Um, how we will measure the conductance? You already know about the measurement of conductance principle. The principle of measurement of conductance is actually measurement of resistance, which we have already discussed in previous courses. That principle we use for the measurement of conductance is actually Wheatstone bridge principle or Wheatstone bridge method. So this can be used for the measurement of conductance. The basic principle of Wheatstone bridge, you already know about this. We have discussed this in previous course of electroanalytical chemistry, and also we have discussed this in spectroscopy course. So we can sorry, in chromatography course where we were discussing about the thermal conductivity detector, and I told you about the Wheatstone bridge principle. The method of measurement is actually the solution whose conductance we are going to measure is taken in the conductivity cell. It is known that the conductance varies with temperature. Therefore, we are abide. It's very necessary to keep the temperature of the solution constant throughout the experiment. This is achieved by placing the conductivity cell in the thermostat, which is maintained at a constant temperature. The cell is connected to a resistance box R on one side and to a long thin wire AB stretched along a scale on the other side. Now some known resistance R is taken out of the resistance box and an alternating current is passed through the solution with the help of the induction coil. Sliding contact, which is denoted as D, is moved on the wire AB so that minimum or no sound is heard in the headphone. And now we will have at this point the relation like the resistance of solution over resistance R, the total resistance. equal to length of BD over length of AD. So the knowing the R, we know the R applied resistance, we know AD, we know BD. So if we know all these the three quantities, then we can find out the resistance of the solution by this relation. Since the conductivity of solution, we already know that conductivity of the solution is reciprocal of the resistance, that is equal to 1 over resistance of the solution. So the knowing the resistance of the solution, conductivity of the solution can be calculated, because this is just the reciprocal. And the next we have how to determine the cell constant. The electrodes in the cell are not exactly 1 centimeter apart, and may not have surface area of 1 square centimeter. So the value of observed conductivity is not equal to the specific conductivity but proportional to this. It is important to calculate a factor for the conductivity cell, because this area is not exactly 1 square centimeter, and the distance between the two compartments of the cell, between two electrodes of the cell, is not exactly 1 centimeter. So we can find the relation which we can use for the further measurements in conductivity in conductometry. So that relation we will find, or we will calculate a factor for the conductivity cell that will be known as cell constant. The cell constant, when multiplied by the observed conductivity, that gives the true value for specific conductivity. This is already mentioned that R is equal to delta into 1 over A, where R is equal to delta X, where X is equal to uh, 1 over A is equal to cell constant. So the X is equal to cell constant equal to R over delta. So the cell constant is equal to, we know that R is resistance, which is reciprocal of the conductivity. So we can write 1 over observed conductivity for R, and delta, we know that this is the specific resistance. So we can say that this should be equal to reciprocal of the specific conductivity. So we can write 1 over specific conductivity in the place of delta. So we can say that cell constant is equal to 1 over observed conductivity over 1 over specific conductivity. So specific conductivity is equal to cell constant into observed conductivity. So this way we can find out the specific conductivity. The cell constant is determined by substituting the value of a specific conductivity of a specific solution, normally n by 50 KCl solution at temperature 25 degrees centigrade. So this value is already determined by Kohlrausch, which was 0.002765 milliohms. The value of conductivity is then observed with the given cell using N by 50 potassium chloride solution. The cell constant is then calculated by using the following relation. So we can say that cell constant is equal to 0.002765 divided by the observed conductivity. So this is all about the relations between different terms, and to calculate the conductance and cell constant. And then in the next lecture we will move towards instrumentation.